Hello viewers, you are welcome to this video lecture. I'm here to present the 21st video lecture from chapter 6. Chapter 6 deals about the drainage and drainage structures. In the previous video we have deals about the importance of drainages and also deals about the surface drainage related to the flood estimation and the hydraulic design of surface drainage structures like open channel and culverts will be deals in the previous section. Today's will be deals about the subsurface drainages. In this main topic is the design of subsurface drainages as well as determination of discharge quantities will be discussed in this video. First will be deals about the surface drainage systems are provided within the pavement to drain water that maybe the sources are three. The first is percolated through the cracks and joints in the pavement. So this one is the source is mostly the rainfall water, so percolated through cracks, and also he move up through the underlying soil stratus, also like a result of capillary actions is the second source. The third source is related to the natural ground below the water table. It is refers as groundwater is the sources of the subsurface drainage. So the design of the subsurface drainage should be carried out as integrated part in design of the highway. Inadequate subsurface drainage is very serious in stability of slopes and also the pavement performance. So there is a subsurface drainage is not adequately provided, so the subgrades will be softening and there is a large amount of moisture, so this moisture will be lowering the strength of the structures. The process usually adapted for surface drainage design is first determined the geometric and structural requirement of the highway based on the standards. For example, Ethiopia use the ERA manual for determine or analyze the surface drainages. It is extremely difficult. It is not impossible for providing and solution for the mostly the surface drainage. It requires more practical engineers or laboratories will be required or take into account for the problem will be mitigated. The surface drainage systems are usually classified in 5 major categories. The first is longitudinal drains. It is mostly provide parallel to the center line. Transverse drainage will be provide for subsurface drainage systems. It is provide perpendicular to the center lines, and horizontal drainage mostly used percolated pipes. Drainage buckets also will be used. A large amount of thickness is provided, and systems also will be provided. So we have discussed each of them. So the first one is longitudinal drains. So this longitudinal drains will be usually consist of pipes laying in the trenches within the pavement structure, and mostly it is parallel to the center lines of the highway. These drains can be used to lower the water table below the pavement structure as shown in the figures. In the figures also will be show this there is a longitudinal drainage system. So this one is a longitudinal drainage system. Is also this one we longitudinal drainage systems. So it is always parallel to the center line of the pavement. So this one is also will be the second part is it is a traverse drainage, so going to longitudinal drainage. And traverse drainage is mostly difference from the longitudinal drainage is because of it is perpendicular to the center line. An examples of the uses of traverse drainage is shown in the figure. So there is a road, so perpendicular to the road, so we provide traverse drainage system. It is percolator pipes. So this one is also uses our percolator pipe. So provide it is more we have it is perpendicular to the center line. This also you use, so it is a percolator pipes. So we have placing it is perpendicular to the center line is this one. So we are placing the traverse will be perpendicular to the center line. So there is provide longitudinal drainage. So collect from the traverse drains. Horizontal drain mostly will be this is a percolated pipes, mostly used for in slope of cuts and embankments on the highway. Most of the retaining walls also will be use horizontal drainage. They usually consist of small diameter percolated pipes instead to slopes of cuts and fillers. So in the figures also we'll have this one is the horizontal drain. So the horizontal drainage will be drains through to the longitudinal drainage, and the drainage blankets also will be dealers. The drainage blankets is a layer of material that is very high coefficient of permeability laying on the pavement structure with the widths and the lengths in the flow direction are much greater than its thickness. The coefficient of mostly the drainage blanket is related to the coefficient of permeability. The coefficient of permeability is the constant proportionality of the relationships between the flow velocity and the hydraulic gradient between the two points. So mostly the blankets can be also be used in conjunction with longitudinal drainage to improve the stability. So the drainage will be the drainage blankets will be connected to the longitudinal, so collecting the waters from the underlying the pavement structure to the longitudinal. So this one is the drainage blankets. This thickness, it is mostly it is percolated, so the it is moving to the longitudinal drainage. In this case we will provide longitudinal drainage, so we have provide this is a longitudinal drainage. So the design of subsurface drainage will be the design procedure for subsurface drainage involving the following steps. The first is summarize the available data related to the subsurface drainage systems, and determine how much and also the quantity of waters for which the subsurface drainage system is being designed, and also determine the drainage system required is determine the capacity and spacing of longitudinal traverse drainage. Lastly will be evaluate the design with respect to the economical visibility. So summarizing about the available data, so the first available data is the flow geometric. The flow geometric is given by the existing subsurface characteristics of the areas related will be the highway location, the sizes, also the related to the geometric also is summarized as the flow geometric, and also the material property is very important. It is related to the permeability. Hydraulic and climatic characteristics also will be related. The first indicator will be precipitation rate. So there is a high amount of precipitation. The water, the discharges also will be increased, and the source of subsurface the waters related to the percolated, related to groundwater also will be calculated. Miscellaneous information is or the other information is lying in the design of effective and economic subsurface drainages, including any impacts in structured drainage system will be further constructions. And also will be the second steps will be determine the discharge quantity. So we calculate the discharge quantity. First will be the waters due to infiltrations, the groundwater, the water due to melts. It is mostly in tropical. In Ethiopia case there is not significant problems, and the water evaporating vertically from the pavement structure will be considered. The first one we consider the waters due to infiltration is very important. So we have calculate the infiltration rate. These sources is coming from the cracks percolated from the surface pavement surfaces. So this one is calculated as using these formulas. So the discharge infiltration rate is equal to the crack infiltration rates will be mostly will be used 2.4 feet cube per day per fetus, and also we have used the number of contributing longitudinal cracks. So the number of traffic lanes will be considering. The width contributing traverse cracking also very important in feet over the width of the granular bases times by spacing of traverse cracking, and also plus the rate of infiltration is very important. The second is the source is groundwater. The groundwater is possible to anticipate the flow of groundwater or lowering the water table is sufficient before the water is reaching to the pavement is very important. So the amount of groundwater seepage also will be calculated by using these formulas. So we have used 3.8 times the thickness of the grades below the drainage pipe and minus the thickness of the sub grades below the natural water tables. As you know, is shown in the figures, there is the level of water. This the original ground level. This one is pavement structure. So there is groundwater is in this level. So in this level, so we have going to the pavement. So lowering this water table, and we have provide surface structures. So this one is gained by Q1 and Q2. Q2 is the height of the elevation is the quantity of waters under the surface. This Q1 is before reaching to the pavement. So H will be the total thickness. So half of the width of the road center line. So we have using K infiltration rates H minus H naught, the thickness over 2 times Q, the discharge. So we have done these empirical formulas. So there is infiltration rates plus 0.5 times W is the width, and HO. So we have gates, for example there is 5, so K values will be 2. At this point we have determined W over H naught is equal to 1. so in this case will be 2. And also will be the third step is vertical outflow or evaporation. In some cases, the total amount of water accumulated within the pavement structure can be reduced because of insignificant evaporation of some of the accumulated water through the subgrades. So net the design flow will be, if there is no frost, so we have no groundwater and no arterial flow, and if there is no flow and arterial flows will be calculated by second formula. So we have using depending upon the frosts and the groundwater will be those cases. And design of the drainage layers is very important. So the design of the drainage layers will be by using determined by the maximum depth of flow. If this will be using permeability is known. In this case, the permeability is it is required. The maximum flow is known. So we have used the two cases. The drainage material should be consist of sound, clear, open graded for the purpose of high permeability. So and also we'll have the amount of fine particle using in the drainage layers affect the permeability, or it is clogging of the holes. So this one is decreasing the permeability. So using the perfect or suggested grain size is very important. So this one is calculated by K will be the permeability is equal to the effective grain size D10. 10 means 10% will be passing a given sieve size. And also the Hansen coefficient is provided for very important. So another approximating will be using empirical formulas. K value permeability is equal to 6.216 times 10 to the power of 5 times D10. It is effective grain size corresponding to 10% passing. The power of 1.478 and times n will be the porosity, the power of 6.654 divided by p 200 means the percentage fine passing will in the sieve of 20 sieve sizes, or the power of 0.3947. so we have getting the value of the permeability, and so we have calculating the permeability by using these flow charts. So design of longitudinal collected pipe. So the thickness already will be calculated. So the collected pipes, percolated pipes also will be calculated. So this will be calculated by a circular pipe are generally used in longitudinal collectors, are usually constructed either by porous concrete or percolated corrugated metals. So the pipes are laid in the trenches located at the depth that will allow the drainage of the subsurface waters from the pavement structure. So the trenches are the backfill. So we have critically will give attention for the size of or the diameter of the aggregate is very important. So the designs of longitudinal collectors involving the determination of suitable backfill material by using this formula. N is Manning roughness coefficient times the discharge times by the length between the outlets. So the slopes and the diameter also very important. So from these calculations will be get the longitudinal collectors determination for the suitable backfill materials. D values will also be calculated by using this formula. Alternatively, the charges shown in the figures below can be either to determine the maximum pipe diameters and also the distance between the outlets. The gradient means the slopes also will be calculated. So from the charges first determine to the amount of the flow times the length between the outlets or the flow paths. We also will be calculating by using this formula. So there is pivot lines. So from these lines will be determine the distance between outlets. In this case, 500 feet. So we have going to the flow rate. So the flow rate is 25. So and also will be corrugated pipes also will be use the same pipe gradient. The slope is 2%, for example. So the examples will be the discharge is 25, the length is 500, the grade will be 0.02 or 2%, and the diameter is 4 feet. From the material selecting to the backfills in the pipes, it is coarser than the hole, the diameter of the hole. For slotted pipes will be D85, means 85% will be passing filter over slots widths, and for circular holes also will be using D85. 85% will be finer or passing the given sieve size over the whole diameter, so greater than 1. It is for example, it is less than 1, the hole will be greater, and small, and the aggregate will be greater. For example, it will be the hole will be small, so the pipes will be greater. So we have mostly greater value. The filter criteria also very important. So fine grade soil particles from subgrade soils adjacent to the drainage layers may be transmitted and clogging the voids in the drainage material. So this will be finally reducing permeability, so decreasing the permeability, so there is closing of materials, the holes, so totally subsurface drainage is a problem. So clogging criteria, D15, 50% will be passing filters over D85 protected minus the soil is less than 5. It is clogging. Greater than 5, there is clogging, there is the material will be not permeable. Permeability criteria is greater than 5%, and also will be additional criteria making the grain size curves of filtration also protect soil somewhat parallel. So we use D15, 50% will be passing filters over D15 protected minus soil. It is less than 25 will be very important, and the filter materials have a coefficient of a uniformity. D16 over the D10 is less than 25, so the amount of fineness, so this will be protecting the holes. The holes will be larger, the material will be low, it is a clogging, so totally the subsurface drainage system is fails. So in subsurface drainages the diameter is very critical. Thank you for listening.